Very good. Okay, so welcome everyone. Thank you for attending. I think I recognize at least some of you from the first session from a couple weeks ago, as well as some new faces today. So I'm excited to continue this workshop, this machine learning primer workshop that is supported also by CIRCA Ateliers. So thank you all for attending in person, as well as all of you who are currently on Zoom as well. As some of you may have noticed, once again, everyone in person is aware that our venue is slightly different from last time due to some technical weird issues with the room we were in before. So if I look a little bit different and my background's different on Zoom, that's why. Hopefully we'll have that fixed by the next session as well, but otherwise we'll certainly make do with what we have. So our topic for today is going to be a survey of machine learning models, and then I will describe in more detail neural networks in particular, as well as more specifically the training of neural networks. And then I'll go on to discussing the process of gradient propagation and update rules. So I want quickly to give either a reminder or perhaps a quick introduction to what was covered in the previous session. We did talk about traditional data analysis methods, specifically with data decomposition and dimension reduction techniques, such as proper orthogonal decomposition in the form of PCA or SVD. And then we briefly went over various sort of traditional clustering methods, such as k-means or k-nearest neighbor. And then for the second half of that, we went into a bit more of an introduction of general machine learning concepts, such as what types of data you might encounter, input data labels, so whether you have supervised or unsupervised setting for your learning, and then what different objective or loss functions you might encounter, and the problem types associated with those loss functions. And then finally, we looked at how you might evaluate a model and the process for sort of setting up your data so that you can perform that evaluation. And in particular, I just want to highlight these last 2 points because we'll be developing those. They'll be very much related to particularly the training aspect of what I'll be talking about today in this session. So for today, our focus is going to be on, as I said, a brief overview of various machine learning models that are not neural networks. And so this is just a survey, so I'm not going to go into extensive detail, but of course, if anyone has questions they'd like to know more about, please feel free to interrupt and just ask at any point. But I'll start by going over linear, polynomial, and logistic regression, and then explain a bit about what state vector machines are and how they're used, and then give a brief overview of decision trees in random forests. And then the bulk of this session will be focused on neural networks in particular, given that they're sort of the primary tool used in many of the modern and advanced data science and machine learning applications today. And then in covering neural networks, I will start off by going over what the general structure and the equations are for neural networks, so we see what the framework is for that. And then I'll describe how we train neural networks through, in particular, gradient propagation or gradient backpropagation. And then finally, we'll discuss what kind of rules are used in order to perform the updates to the parameters of a neural network in order to achieve that training. Okay, so I'll get started here then with that survey, as I said, starting off then with our linear and polynomial regression models. So now I will say, as a reminder, for those who didn't attend the previous session, my goal, while I will have some equations every once in a while, my goal is for this to be accessible to everyone, regardless of what they have a math background. So I will be going rather math light on a lot of this, but of course I will gladly, as someone with a math background myself, I will gladly go into more detail here, but I'm trying to fight that urge and really be as accessible to anyone as possible. So this is admittedly probably the most equation heavy slide, so you're welcome. Yeah, so just be aware that I will try to make this accessible, but if you have any questions about the details of any of this, feel free to stop me at any point. So the idea behind linear regression is that we're seeking these linear coefficients beta sub k, which are going to minimize our residual, which is given by epsilon in this equation that's shown here. So if we look at how things correlate to this figure down on the bottom here, we have our true labels are given by the points in red, so that's our y sub I, and then we have some sort of prediction or our function, and so this is where the linear regression comes in. It's linear regression because our prediction ends up being a line, and then the difference between those is going to be these residuals or these epsilons that pop in here. So the weight that we assign, or effectively the slope that we give to this line, is coming from these different betas that we're assigning to the different values of x. And so that'll come, you can write this more succinctly in the form here where we consider this matrix product with a vector. So if we consider this beta to be a vector consisting of beta 0 through beta sub p, and then our epsilon will be the residuals associated, where it will be epsilon 1 through epsilon n. Then if we consider our data matrix X, which could be multidimensional, and then it's going to have a number of data points sampled at different points, then if we perform, like, we'll be performing this multiplication in order to get what our prediction, that will be our prediction, and then that will give us our approximation of what y is. Now this concept I've been describing in this product here is really, I'm switching over to laser pointer for zoom. This product here of the x times beta, that is linear because we're only considering the first order values of this x, but this can then be extended to polynomial terms where we can choose some polynomial, higher order polynomial of order k, where we just have to continue this process where we have our superscripts of this beta, which is just referring to the coefficients corresponding to a certain order of our x. And then if we just take each individual point, so the power here is representing an element-wise power for each of the points in our data matrix, then we would find the combination of these of all of these weights that we need in order to solve for this prediction here. So of course, I mean, the examples that I'm giving are really just one-dimensional examples. So it's not like our matrix beta is, or our vector beta is actually just going to be like a beta 0 and a beta 1, because we have a 0th order term, which is a constant, and then our first order term, which is just x. But we don't have a large number of points there. Like we don't have a higher number of dimensions there, so it's not super complex here. But if we wanted to consider a polynomial term here, where the green here on the right side is actually representing a second order polynomial or quadratic, and then we have the third order polynomial in yellow, so a cubic, where in that case we would need to include the beta 0 term, the beta 1 term with x to the first, and then the beta 2 term for x to the second. If we're doing the quadratic, we'd also need the beta 3 term with the cubic term in order to solve for the cubic one here. So that's how we extend linear to polynomial regression, which is, as using the lingo that we used in the previous session, as you can imagine from the top here, this is a regression task. But then we can extend it to logistic regression, which somewhat confusingly is not actually used primarily for regression tasks, but actually for classification tasks. And the way this works is we're performing a similar function here where we're seeking the weights and the bias that we need here. So this W represents the weights that we're associating with our inputs X, and then we have some additional bias that we're trying to learn. But then we're going to end up using this latent variable Z, or effectively like this, you could plug this in directly, but I like to think of it as we have this additional variable that we're learning in the X, or that's a function of X, which then will be plugged into what's called our sigmoid function, which is going to be outputting a value between 0 and 1, which is representing the probability that that particular input corresponds to the class in question. So in this example that's shown on the right-hand side here, where we're looking at a particular class where you are considering based on how many hours a student studies, what's the probability that they pass that course. And so in this case, we have really only two classes we could be split into, where pass is one class, and then fail is the other class there. So in this case, the sigmoid function would be outputting what's the probability that you are indeed passing, which is what's shown by the blue curve here. However, that's only considering, in many classification tasks, you're not only considering 2 classes, but could have a greater number of those, in which case we can extend this sigmoid to what's called the softmax function, where you can have, in this case, an uppercase K or capital K number of classes, and you are looking for what the most probable class is by finding the maximum value over our Z's. Over our I's. So you're trying to find the class for which the softmax value is the greatest, and then that would be the class that you would select in this classification task. So once again, a little bit confusing that logistic regression is not really a for regression tasks, but it still is based on your learning the associated W's and B's in this function here in order to develop this sigmoid function to predict those classifications. But then we can extend this where it might not be so clear when working in a single dimension how exactly to split 2 different classes. So in this example I'm showing here, we have both the blue class and the red class, but those 2 classes are not necessarily, there's no single line that you could draw in here in order to separate those cleanly. So one thing you could attempt to do here, and what's the idea behind a support vector machine, is that you can introduce a function or a kernel in order to add additional dimension or dimensions in order to make that data separable. So for example, if we introduce a quadratic kernel here, this allows us to separate out the data in this additional dimension such that we can draw a single line that will separate out these two classes. So we call that a hyperplane in this space that leads to a separation between the blue class and the red class. This hyperplane will be defined by the following function, where we have this W. This W is representing our normal vector, or what's called in this case the support vector, hence support vector machine, which is what is trying to be learned such that this space between those 2 points is maximized. And then we'll have an offset, which is simply going to be this B, which tells us sort of how much it's moved from how much that plane is separated from the origin there. So this can be a very powerful tool, like a very powerful classification tool, but you do have to choose for yourself what that function is that you use in order to find this additional dimension. So then another common model that can be used oftentimes in machine learning will be decision trees. So the way decision trees work is you start with a single node up at the top, this root node, which will look at all the data and find a way to split that data such that decisions can be made based on them depending on what your desired output is. And then at different stages, it will then continue to do that recursively until it's able to find like an optimal separation depending on some of the constraints that you might place on it. Now, most of the time, if you see a diagram of a decision tree that's not on a real example, it might look nice and balanced like this, but that's not a requirement for a decision tree. It can be very imbalanced. You can have it where maybe 60% or 80% of the data gets put to one side, and so it has many more, it might have to go through additional steps in order to reach that decision boundary at the end. So when it reaches the end of this tree, the output of these, what's called the leaf nodes, will be some sort of prediction or some sort of output, depending on what your desired outcome is. But in practice, oftentimes, these decision trees will be built on and actually used in an ensemble of decision trees in order to form what's called a random forest. And so what this will do, I mentioned that you can get a single prediction from one decision tree based on a single input, but random forests allow us to sort of reduce overfitting and build more robust predictions to outliers by aggregating the predictions across a variety of decision trees or that are operating on different subsets of the data to then give us a sort of collective and democratic output. Sometimes is the way that it can be said. So ultimately, it'll take in the input and then give you sort of a prediction based on what is the most probable outcome based on the however many trees you've collected into this forest. So that's our survey of the previous, of sort of a lot of standard and traditional machine learning approaches. But then I want to focus now for the rest of this session on neural networks in particular. So we'll start with an outline of sort of what neural networks are. I'm sure most people at least have some degree of exposure to what neural networks are, but I'd like to go into them in a little bit more detail to lay the foundation for the rest of this talk. So ultimately, what makes neural networks very powerful is the fact that they're a composition of nonlinear functions. So both aspects of that statement are very important because nonlinearity gives so much flexibility to how that function can respond to so many different patterns or patterns in data and extract things in a way that linear functions are just inherently not capable of doing in a lot of ways. There are drawbacks to that because it means that oftentimes it's a lot harder to interpret nonlinear functions. What's very nice about most linear functions is that they're inherently invertible. So for any of those mathematicians out there, like it means that you can find the inverse function to it much more easily. It may be true to some extent for nonlinear functions, but it's not guaranteed to the extent that it is for linear ones. By introducing these nonlinear layers, which we'll call hidden layers, because in many of the other models that we'd be looking at, instead of having this layer of hidden in between, we'd simply have a direct mapping from the input to the output. So by introducing this flexibility, this hidden layer in between our input and output, it gives so much additional flexibility as once again to how that data can be represented and transformed in order to find these patterns and make these predictions. And an interesting note about neural networks is that there is a theory that's been well proven at this point that with a wide enough or large enough neural network, any function can be estimated to an infinite precision or to effectively be perfectly accurate. And that's in a theoretical limit, but it just helps to demonstrate that regardless of your function, it is possible through these functions to recreate it using a neural network. So I have represented these as equations. As I promised, this will be equation light, but at any time I have an equation going forward, I will break down what each of the parts is so that we can understand it in more detail. So as I said, this is a composition of functions. So I'm going to start with what the first function is performing here as we go from the input to the hidden layer of our neural network. So the input is represented by this x here, which then gets multiplied by the weights, which I usually visualize as the lines that are in between our different layers. And then there's a bias that gets added at the end, which is just like, that's in vector form. And then we have some sort of nonlinearity, which is this activation function here. So I'll describe what forms these can take in a future slide as well. So I just want to point out that this input will be in vector form, and then these weights will be in a matrix form. So since we have a matrix times a vector, that will be another vector, which may or may not be the same dimension as the previous layer. So we have that flexibility. So in the example I'm showing here, our input is of dimension 3 because the input has sort of, as represented by the 3 circles or 3 neurons in the input layer here. But then our hidden layer is going to be represented in a 5-dimensional system, which means that our weight matrix will be a 3x5 matrix, so that as it is a 5x3 matrix, so that as it's multiplied, it will output into 5 dimensions with an input of 3 dimensions. Now, the output then will be once again in a 5-dimensional space, which is what I'm calling this H1. So H representing that it's the hidden layer. But then as we move on and try and determine what our output is, this itself is not a prediction because our prediction needs to be, in a 2-dimensional space, as shown by the green circles to the right. So then we need to compose this function over to the right, where we maintain many of the same sort of corresponding aspects that get mapped. So we have a new bias, but it still is a bias. We have our weights as well, which will be a different map because they're going from 5 dimensions to 2 dimensions. And we also have an activation function, which may or may not be the same, using the same function as the previous layer. But then importantly, the output from the previous layer, from the hidden layer, becomes the input for the layer that will go to the output. And then once again, now the overall output of our system is the Y once that function has now been composed on our previous output. Are there any questions about this setup so far? I realize there's a decent number of moving parts, but I want to make sure this is clear to people. Okay, great. I mentioned, and one thing I've been emphasizing a lot about neural networks is the fact that they have a lot of flexibility, which is both helpful but also can be very challenging. So I want to start by just outlining some of the things that you can vary if you're, sorry, there's a question here.
Sorry, I have a question that's not like exactly related to the current slide, but how would you explain what the difference between like a neural network and machine learning is, like in general?
That's a great question. So the question in the room is, in general, how would I describe the difference between a neural network and machine learning in general? And I would say machine learning, I'd say, is a big umbrella for a wide number of techniques or of models that you can use. Generally, the idea behind machine learning or statistical learning is that you are taking a large number of samples or of data points, and then allowing a model to effectively learn what those weights are, or what parameters they should use that interact with that input data to provide the best possible prediction, or align most with the label associated with that data. Neural networks are, I would say, like they're a particular model that can be used in order to do that, like I said, they're kind of they're very commonly used right now because computational power is very much more accessible than it used to be before. So even though it is computationally heavy compared to many of the previous approaches that were much more commonplace before, comes at less of a premium now than it used to. And what we gain from that computational power is, like I said, this flexibility, as well as a lot of it's parallelizable, so it's actually very effective on very large data sets as well. So thank you for that question. Hopefully that addresses it more fully.
Yeah.
Okay, great, thank you. So when we're working with neural networks, we have a lot of things that we can change and that we can adjust in order to sort of affect how that representation that is very flexible in neural networks can manifest itself and effectively be able to learn these tasks. But there are some things that we don't directly have control over because they might be inherent to the task itself. And that's true of our input and output spaces. So generally speaking, the task itself is what's telling you, or the data itself is what's telling you what your input and output dimensions will be. So if you have like a task where you're in some rotational space, like maybe a two-dimensional space, and you're trying to predict at this point in time, I'm here, and maybe at some point in time in the future, you want to know where you're going to be. Your input is 2 dimensions because it's your X and Y. And then your output would also be 2 dimensions. You don't really have control over that. Similarly, in a classification task, the number of classes that you have, maybe you can select your data in a certain way, but your data is only going to have a certain number of classes to choose from. So that will fix what your output space could be. And there are some things that can be more flexible on this front, but for the types of neural networks we're looking at today, these are fixed values. However, when the flexibility that really does come is when we're looking at this hidden layer. And so in this example I'm showing right now, we just have a 3-dimensional hidden layer with our 2-dimensional input and 2-dimensional output, but we can change that however much we might want. So we can increase the number of dimensions, or the number of neurons that we have in that hidden layer. And in that case, the number of neurons in a layer will be telling us, we describe that as the width of a layer. But that's not the only way that we can increase the dimensionality of our hidden layer, and therefore of our representation. We can also do it by introducing additional layers. So you don't just need the one, but you can actually have 2 separate layers, such that the representation of your input data can be transformed twice consecutively before producing an output. And oftentimes when you're looking at sort of state-of-the-art or published models that even early on, they will have actually a very large number of layers that might sort of increase and decrease in dimension in order to encourage sort of more rich representations and then lower dimensionality throughout that process. But as I said before, I'm going to try avoiding going into like a ton of detail on specific like very complex examples here before really covering the basics here to start with in these foundations. But then it's not only the number of neurons that we might consider here, but also what's going on with the actual function, this nonlinear function that we've been considering that I discussed previously. So the first thing that we can adjust here is this activation function, which I've been calling A. And there are three main functions that are the most common here. Admittedly, you will be able to find many others, but I want to keep it simple. The first one's called the ReLU, or rectified linear unit. This is effectively, it's very similar to just a linear y equals x function, except for any value that's less than 0 is just mapped to 0. We also have hyperbolic tangent, which goes from -1 to 1, and that will have, it will balance out so that at the extreme values, so when x is close to -infinity, it will be very flat, and when x is a very large number, then it will also be very flat, but has the greatest sensitivity around x equals 0. Sigmoid is actually quite similar in that it has the greatest sensitivity around 0 and then is quite flat at the extremes, but it goes from 0 to 1 and might be more common, especially if you're looking at an output and are trying to, as I showed in an earlier example, maybe trying to predict a probability. And then another hyperparameter that you want to consider, and that arguably is the most of the black magic things in this particular part here, is how exactly you're going to initialize your weight matrices and your bias vectors. And so initialization is saying what is the value that we start with here, or what are the values that we start with here? What are the distributions we're going to be pulling that from? And this admittedly is something that there's like wide swaths of research into how exactly you want to initialize this, depending on what sort of structure you have exactly. But some very common ones you might start with are some variation of a normal distribution or a uniform distribution. And then every parameter, every value in your weight matrix or your bias vector will be sampled independently from the distribution that you select here. So yes, those are the hyperparameters that we'd be working with. I'll take a brief pause here just to give everyone a chance to breathe again. Do we have a question?
Yeah, I mean, just like a confirmation, because I've often seen like neural networks, if you go back to like the visualization of the neural networks, I've often seen like weights as being like visualized as like the strength of which arrow, which like indicates basically like which parameters is like more important. And in this case, if the bias is a vector, then would it indicates the direction of the arrow, like which nodes it goes to in the hidden layer?
That's a great question. So for those on Zoom who might not have heard that quite as well, the question in the room was mentioning that oftentimes the arrows shown in depictions of neural networks can have their size or their weight be representative of the strength of the connection between two neurons. And then the question was also like, what would the bias be in that case? And I will actually use a representation similar to that for the weights in a future slide, so you'll get to see that soon. That is a very fair representation, and exactly why I actually referred earlier to the weights referring to these arrows, because that's a common representation of that. I agree, it is confusing because where does this bias sit in that case? And I tend to view it visually as actually that bias sits effectively inside these circles, because that's only added after the matrix multiplication has taken place. And I actually have my next slide addresses that, at least to some extent, of that order of operations. So I'll go over the next slide, and if you want any more clarification, I'm happy to go over it then, but I hope this might help. Okay, so this is actually very much intended to address a question very similar to that, which is when we see these visual representations of neural networks, how can we interpret that and what's sort of going on under the hood? And it can be helpful also to understand neural networks as what can be called a computational graph, because when these are coded and when these are implemented in software packages, they are interpreted much more as these computational graphs than they are in any sort of like visual representation that we might be used to. So, we might start with our larger, zoomed out version in the top left here, which we can then zoom in on and see that there's going to be some sum taking place with then our activation function, which in this case is a sigmoid. But if we zoom in even more detail here, we have what each of these neurons is doing is actually simultaneous computations or simultaneous calculations operating on this same function that we were showing before. Now, each of these parts, as promised, there's an equation on, so I will once again break down what each of these parts is. We have our input, which is this x, the output from a previous layer, and then these w's form this weight matrix that we have right here, and then an important key is that what is this operation going on between the w and the x? And that is really, it's two things happening in one. We have our multiplication, which is the weight being multiplied by each of the x's here, and then anytime you're performing matrix multiplication on a vector, you also have a sum taking place at the end of that as well. So that's where all of these arrows are taking place. Now, where I think this is hopefully helpful is that you note that the sum that happens here, which is simultaneously the sum from the w, multiplication, as well as the sum from the bias, is taking place inside this circle here. So I think as like a visual representation, I think seeing it in this way can be helpful to disentangle those. And then, as I mentioned, we introduce the bias here, which then has, this sum, the sum circle here is actually doing two separate sums before being multiplied by this, being operated on by this sigmoid function. And one thing I meant to mention earlier with the activation functions, by the way, is this sigmoid is an element-wise operator. It's an element-wise function, but the argument on the inside is going to be a vector. So just think of it where each element in that vector is simultaneously being operated on by this like sigmoid or by the tanh or by the rectified linear unit. So I mentioned I don't want to be too mathy here, but like I hope that for those who have familiarity with that, that might help with understanding some sort of the dimensionality of what we're working with here and how that function operates. And then this output, this h, is then going to be sort of these output arrows as well, which admittedly, when they go to other layers, they'll then also be operated on by these w's. But the output will then go on to these future layers. So as I've been referring to already, these individual components are often referred to as neurons, and as was brought up very well by the question earlier, these weight matrices are really analogous to the connections or the strength of the connections between these neurons. Now, of course, I'm saying these analogies, and I realize I'm speaking to mostly a neuroscience audience here, so don't hold me too much to account in that they're not like perfect analogies, but that's where a lot of the inspiration for neural networks came from, was in observing these connections in the brain. So having seen the general structure of neural networks, I want to go over what the process of training is, where we'll start with inputs being provided to a network through in order to produce some sort of prediction or output. So this starts with a forward propagation pass, where we start once again with an input layer, where, as we were describing before, we move on to a hidden layer and then to an output. That output is then compared to whatever our target or our label is, and then the difference between those is what provides us with the loss. And I talked about loss functions in our previous session, so whatever loss function you're using there will give some value for this loss here. But then we have a second stage, which takes place here based on what value of loss we encountered when comparing the output to the target, which is after forward propagation, we then do back propagation to assign the credit of how much of error comes from each parameter in the system. And so it starts with the loss, and then it gets back propagated back to the hidden layer, and then once again to the weights that are determining the connection between the input layer and the hidden layer. Now there are some, for those who are interested, this comes from the fact that we have what's called a gradient, and that is the gradient of the loss. The gradient of the loss, which can then be decomposed as a composition or as a product of many partial derivatives of all the different parameters that lead up to that. But that would require multiple slides of just equations, so I'm going to spare you of that. But if anyone wants to learn more about that, feel free to reach out to me, and I'm happy to provide resources on that. So the process of training is really, how do we update this network according to whatever this loss value is and the associated gradients of all the parameters, as the network continues to see a large number of inputs. So that happens through the process of what's called gradient backpropagation. So the idea behind this is that we're trying to determine what the contribution is to that final loss from each component or each parameter on the computational graph that we described before. And the gradient is effectively giving us a direction with some degree of magnitude, although the magnitude will be something that we can sort of scale up and down depending on what we choose during the optimization process. But it gives us the direction we need to move in parameter space in order to reduce that loss as much as possible. So if we consider just the weight, the only parameters I want to look at for this network here are hidden to output weights. So that would be these arrows here, and then our input to hidden weights, which are represented by these arrows here. And then, so very abstract in the way that or very like hand wavy in the way I'm demonstrating everything here. But if we have some input that gave us a loss of magnitude represented by this circle here, this red circle, as we propagate backwards, we might say that the contribution to the loss from each of these weights would be assigned according to the size of these arrows that I've indicated here. So what that would tell us is, within the weight matrices here, some of them would need to decrease by a lot, increase by a lot, depending on how much weight is assigned to each of these. That tells us how much each of those weights needs to change. And then that would then be backpropagated further so that we see the corresponding changes also for the other weight matrix or the other weight parameters. And then what this is really telling us is then, if we change these parameters such that at the next iteration they have these new values where they say decreased or increased by the value that is outlined by this gradient, then we would reduce the loss the next time you see that particular sample or the next time you see that set of data. So that's the idea behind gradient backpropagation. It tells you where you need to move in order to accomplish that decrease in loss, because ultimately that's the idea behind training, is to reduce our loss, which is why we defined the loss function in the first place. Now, there are some practical considerations about how exactly do we feed this data to the network? How much data do we give it at a time? You might think our overall objective is, of course, to minimize the loss on an entire data set, because we care about all the data. Otherwise, why would we have it in the first place? So we want it to be minimized across all of it. Now, something very helpful about neural networks is that they can process many inputs in parallel. So it has a lot of flexibility there, because so many of these things are not dependent on knowing everything all at once. You can process a whole bunch of different samples and then find the loss at the end for all of them in aggregate, and then compute that gradient after that. However, if you have a very large data set or even a moderately sized data set, it can be challenging from a practical perspective to actually provide it all of the data at the same time. Many data sets that all of us work with might be gigabytes large. I'm sure many work with terabytes, that kind of thing. You're not going to be able to fit that on your CPU, or for neural nets, oftentimes they're on GPUs. So that would be very challenging to do that. Not to mention, it's not just the data that needs to be stored, it's also all the parameters of the network that need to be stored, as well as the internal representations of the data. So if your data set, even if it's not particularly large, if you have a complex model, that can saturate your computer or your GPU's memory very quickly. So instead, what happens is we would split up our data into batches or mini batches, and then send those iteratively into our network, and then update after each one of those. The image that I'm showing up here kind of gives you an idea of how you might split up your data. So if you have, say, like 1,000, maybe you only, maybe your total data set has 1,000 samples in it, or 1,000 data points. You could split it up into 5 different batches of size 200, and then if you iterate over all 5 of these, so you've fed the model all 5 of these batches, then you will have, we call it a single epoch, because once the model has seen all of the data one time, we say that it is iterated over one epoch, and then oftentimes you will iterate over 10, 100, 1,000 epochs, depending on the complexity of your task. It may require the model seeing the data many times. So to give a brief visualization of how exactly this would work, or what the difference is between providing all of the data at once versus splitting it into batches, I have a cute little animation here for you. So let's say we have all of the data provided at once. We get some sort of output, as shown in the green here, and then it will give some single sort of cohesive gradient all at once that then needs to be fed back into the system, and that gives us our updates all at once based on just a single computation of the gradient. But those were big boxes. It might be a little bit challenging to shove through your GPU all at once. So instead, you might choose to split up into some smaller batches, which then get fed individually, and then perform this operation iteratively each time. Now, what's a little bit different about this compared to feeding the entire data set at once, or feeding a larger batch at once, is that every time that red box was moving to the right, from the right side to the left side, the parameters of the network were updating at each of those steps. So you're not waiting until you've done all of them to perform any updates. That can be helpful because it can lead to performing iteratively, especially in a situation where it might be a little bit complex, can be useful for effectively searching for and finding your loss. And on that note, I'll actually describe how challenging that might be in another slide here. So we can visualize how we are navigating these parameter spaces as we're performing these updates through what's called a loss landscape. Now, this isn't something that in any of your tasks you're likely to have to actually visualize or generate for yourself, but I find that this conceptually can be a very helpful way for you to understand not only what's happening when you are optimizing a network, but also what can be some of the challenges if you find that it's not working as well as you hope. So what is shown on this left side here is a representation of the z-axis here is saying what is the loss, what would be the loss of a network for a corresponding parameter set, and then our x and y-axis are just the first 2 principal components of the representation of your parameters of your entire network. So a single point here would just be, we have in the xy coordinates, it's telling you what are the parameters in that principal component space. So just think of that as that's some instant of values of a parameter set, and then the z value is saying what's the loss at that for those parameters. And so, as you can see here, we have the highest peak is telling us what's the highest loss in this space, and then the blue trough is telling us what's the lowest loss there. So of course, ideally, as we perform this training process, we want to end up at this lowest loss. Now, it is worth noting that your choice of structure for your neural network, depending on what your task is, can be made simpler if you or effectively introducing certain aspects of your model or your network can lead to a transformation of the landscape of the loss function. This example here is using what's called skip connections in a rather complicated task in order to smooth this out. But while I'm not really going to go into any detail in these seminars about what methods are in order to smooth out this landscape, it is going to be very task dependent and very architecture dependent as well. So unfortunately, this is some of the black magic that is associated with working with neural networks sometimes, but it can be very interesting. So I want to go into a little bit more detail of how we actually go about navigating this lost landscape, and maybe how to interpret this type of visual. And so once again, we're considering, if we consider each of these any black point here as just being a certain set of parameters, and then the loss associated with that set of parameters, then as we perform our gradient descent, it'll point in a certain direction that will, based on the point where we are, it tells us which direction should we move in order to most quickly reduce the loss based on where we start. So if we start in this position here, because it's on this ridge or on this slope that is pointing down towards this low valley that's right next to it, it's going to point in that direction. If we start up on this very high peak right here, we clearly did not, we got very unlucky with how we started because we almost are in the worst possible spot, but we can quickly make up that ground because we're on a very steep slope here, and it's pointing down in this direction where we seem to possibly be entering this sort of trough or this valley that's in between here. Now, if we start on this spot that's on the bottom left, that's not quite as steep of a location, so it might tell us, it'll give us the direction pointing down this slope, but the magnitude might be a little bit less because that's a bit more of a flat part of the landscape. There are some interesting parts that can pop up here though, because if we start, say, on this ridge here, and we just happen to be on the side that's maybe on this outside portion here, it can be, if we only do one iteration here, it would actually point us away from what our global max or our global minimum is, and into this area where locally it looks like it's going to give us an improvement. Now this is just individual steps that are taking place, so that's why we need to continue to iterate over a long period of time and seeing the data over a good number of iterations so that it can continue to explore this lost landscape and find what that actual minimum is.
I have a quick question.
Yes, question.
How do you avoid then getting stuck in like one of those local troughs then? Because I suppose with multiple iterations it would just keep hopping around and just kind of end up staying there. How do you kind of break out of that then?
That's a great question. Yeah, thank you. So first of all, that can be where it's helpful. Splitting into the batches can be useful because it means that you're not just constantly reiterating the same exact point. So you can figure you're sampling from some distribution, but you're picking maybe different points, which can start putting you in a different direction. So that's sort of the statistical way that you can view it, where there's some noise, there's some randomness to your data set, which means that your changes and your updates based on that data will be able to move around to some extent there. Now there's another thing that is a great segue, so thank you, which goes into what optimizer we might end up using and how we use that optimizer, because this is ultimately, it's all based on what that gradient is that we computed. That's based just on the neural network itself, the structure, the architecture that we defined for the neural network. But then how we choose to use that gradient, exactly how we choose to update our parameters based on the direction that it points us in and the magnitude that it points us in, that's defined by what we call optimizers. So your standard optimizer, or your sort of like very vanilla optimizer, is called stochastic gradient descent, or you might call it mini batch gradient descent, where it's just going to be performing it based solely on which direction that points in. You do have something called a learning rate, which will tell us like how much should we scale that up or down. Oftentimes you'll have learning rates of 0.1, 0.01, something like that, which says, okay, I know you say you should end up way over there, but like, let's just go 10% of the way. And then, because we know that we have to see a whole bunch more data, and then eventually that might accumulate and get you there in time. But generally you want a low learning rate, so you're not like jumping around a whole bunch like really fast, because generally the idea is like if you bounce around and take a whole bunch of small steps, that will at least eventually put you on that path. There is another aspect though that you can introduce to your optimizers in order to avoid some of these valleys or some of these troughs that are not the global minimum, and that's by introducing something called momentum. Now this gives you two two effects that can be very helpful and useful. So the idea behind momentum is that it's something that will accumulate over time. You can think of it as we have some degree of acceleration that's taking place, where if you have a certain component that is popping up consistently over and over for the direction of your gradient, then it will, then you want to encourage that future updates will incorporate that component more or prioritize that component more than the ones that are changing very rapidly. So they aren't developing any momentum if you're constantly going back and forth in sort of opposite directions. But if you have a component that is matching up across each of these updates, then the idea is, well, we want to keep moving in that direction because that's the most probable to actually be the direction of the minimum. So that's what we're demonstrating here, is that you converge at least a little bit faster and more efficiently when you introduce this momentum where you continue in that direction. There's another aspect that can be very useful with that, where this animation, of course, is at the very end, but once it restarts, where momentum can help you get over the local minima by encouraging that you keep moving forward. And then once it, because it maintains a component in that direction, so it can get past a local minimum, but then if you have, admittedly, you can still have another local minimum that it might get stuck in, but it requires considerably more of sort of, you might think it needs more energy for it to escape that local minimum, which means it's more probable that that is either the global minimum or a stronger local minimum. So that's what introducing momentum can do in order to overcome some of these issues. Now, admittedly, like getting out of the sort of difficult loss, like the difficult portions or areas in your loss landscape can be very challenging, and oftentimes it actually comes down to initialization. So it actually comes down to where do you start, being just as, if not even more important than how you navigate that, because there are some parts of the loss landscape that are just impossible to get out, or highly improbable to get out of without without seeing literally the exact right data, and even in that case, it might never happen. So that's why initialization is also part of the black magic, because you have to figure out where to start in that space.
Could I also ask, so let's say you're done with your training, is there a way to test then that you have reached that kind of global minimalization of loss?
No, not really. Ultimately, that's where training a good number of models and using a validation set and a test set or something in order to perform that check. So that's usually what the purpose, especially for neural networks, that's where validation sets and this process that was discussed a little bit in the previous session, that's where it becomes really important to do that. And technically, you never really know that you've hit the global minimum. I mean, you can have a lot of confidence, and usually, you can base it on whatever loss function you're using, what's reasonable. You can look at, oftentimes you can see at the accuracy of the predictions, and usually you don't, what matters most is really like, the ultimate performance. Yeah, I mean, that's a great question. Like like I said, usually it's just going to come down to training a large number of models with different combinations of initializations or different hyperparameters. But yeah, ultimately, like, you're not really going to be able to, it's really impossible to like generate an actual like loss landscape visualization like we saw in that previous slide, because that would require like training thousands or millions of networks just to like get each point with that kind of precision. But thank you, that's a great question. Okay, I just have a couple more slides here, and I know I'm running low on time, so I'll try and go quickly here. I want to throw this, I have this slide in here specifically because I know I'm talking to a neuroscience audience, so I want to bring up some of the possible issues that can come up with gradient descent. So notably, gradient descent is a global update rule, meaning that all parameters in the system are updated simultaneously, and they're also updated regardless of sort of the spatial relation between these parameters, which has often been criticized as being biologically implausible, because it effectively says you have infinite speed information transmission within this network. So ultimately, it's rejected by much of the neuroscience community if used as a specific mechanism for how the brain might perform updates. So other methods are adopted for training of neural networks that can be that have more of a biological inspiration, and so that one such rule would be based on Hebbian learning. And I was thinking of trying to include the equations for Hebbian learning in here, but it's many layered, so I'm going to hold off on that so I don't crowd it with too many equations here. But effectively, to summarize how it works, it's based on correlation between the global reward, so whatever your output function is. Global reward is effectively the inverse of a loss, and then the activity of nearby neurons. So really the idea behind Hebbian learning, and the catchphrase behind it is often neurons that fire together, wire together. So you're looking at the correlation between the firing of nearby neurons and seeing if it aligns well with that loss function. If they do fire together and it aligns with the reward, then the strength between those neurons would become strengthened. Or sorry, the weight between those neurons would become strengthened. Okay, I just have one more slide here then. So I was mentioning a little bit, and as we brought up in the previous session as well, one major issue that can come up in a lot of functions and is actually increasingly a challenge in neural networks because they can have so many parameters. You really need to be wary of avoiding overfitting. And so we have sort of, our classic example of overfitting that can happen on this left side here of the figure that I'm showing, where you're trying to find a simple boundary between our two classes. And if you if you have a completely unconstrained solution to that, then you might have this really convoluted boundary that weaves in and out in between, and that could lead to, while it is helpful for explaining that data specifically, it might be sort of overdoing it and making future predictions inaccurate. So one way we might represent a solution like this in our neural network framework is that we have some parameter set that has weights that I'm associating with these circles that I've drawn right here. And it's based on some single loss function, which is completely unconstrained and has no regularizer associated with it. But we might look for certain kinds of solutions through this regularization based on what we might expect to see. So one type of regularization we could introduce is called L1 or lasso, where we assume that only a small proportion of the parameters in our model are important for making predictions. So then we would minimize the other ones. So mathematically, it would be represented by this term shown right here. We have a lambda, which just tells us what's the strength of this regularization. If we really want to enforce this and have this be the most important thing, we could set that number very high. Or we say, okay, this is a weak regularization, I'll set it very low so that it's not overriding too much what our loss function is saying these parameters need to be. So the way that might transform this particular parameter setup is that the ones that are already somewhat small would be minimized further because we're looking for a sparse representation in this parameter space in order to find what our solution is. So L1 is really looking for a small number of, a relatively small number of parameters in order to make these predictions. So there are some cases where you might find, or you might expect that to happen, in which case you'd introduce an L1 regularization. Another one, sort of on the opposite end here, would be L2 or ridge regularization. The key to this is that we'd be avoiding assigning too much weight to any individual parameter at the expense of other parameters. So generally what this will do is you can think of it as like rounding out or evening out the contribution across a large number, across your parameters, which is saying you expect a relatively equal or balanced contribution from the different inputs that you're seeing. And so that's why you'd want to balance out the weights that you have using this L2 or ridge regularization. And so as you can see here, instead, the ones that were small become a little bit bigger and the ones that were bigger become a little bit smaller in this regularization. So note that even though if we're just looking at the loss function, it would mean that this loss function would be in all likelihood, because we introduced a new term and a new constraint on these parameters, our loss value would be higher in the training process. But when you're looking at these regularizers, where you will see the advantage is when you're performing that validation that takes place later, because it will improve your ability to generalize from not just the data that you've already seen, but to data that your network hasn't yet seen. So that's how you test whether regularizers are actually effective and are actually helping you out. Otherwise, if all you care about is minimizing the loss on your training set, this is gonna seem like it's gonna hurt you, but well, like I said previously, the validation set is really where you evaluate the quality of your model. So I realized that was a very full session. I'm going to, that was my final slide. I realize we're at 5 o'clock now, so anyone who has questions, I'm happy to answer questions now, but I also feel free, I realize it's 5 o'clock on a Friday, so feel free to head out. But thank you all for coming today and listening to this talk.
So you talked about kind of the different dimensions of the hidden layers, and you kind of briefly touched on some of the points on like why you may want to change that sort of architecture, but do you have kind of like a simplistic explanation for why you would want maybe increased depth versus width?
Yeah, so I would think of it as increased depth. Effectively what that's doing for you is it's giving you multiple iterations of transformations that are like, so I'm struggling right now to think of like examples for exactly when you do that, but sometimes you might find it that that using just like a single hidden layer would maybe like, if that's not giving you enough yeah, like giving you enough representational flexibility. Now I know that increasing the width and increasing the depth each gives you that flexibility, but sometimes like, you know, you can think of it as like, maybe you increase the number of dimensions by having your first hidden layer be a 5-layer, you know, 5-dimensional 5-layer or 5-neuron layer there. But then perhaps, you know, in that space, you have now a new representation that is helpful, but is not fully separable yet, or is not something that's like, you know, that quite gets you there. And oftentimes, like, you're going to have rather deep networks for more complex, for the more complex data and the more complex tasks that are being performed. And so having those layers, you can think of it this way where, like, a new layer is effectively introducing an entirely independent function that is learned separately from the layer before it and has a greater degree, you could say, of like abstraction from your original input. So if there are very complex things that need to be learned and maybe that require multiple levels of transformation in order to extract and like, you know, separate out two things that are maybe very similar, where just projecting into a higher dimension might not be enough, then that's where additional layers would come in. And oftentimes that is kind of the idea, is the deeper you get into a network, usually the more abstract the representation is. So that's why you want to have that. But then the larger ones means that within that representation, you have more flexibility and more ways that things can be grouped around and figured out how to make that work. Thank you for that question.
So how would you choose, like, do you just like eyeball it, like the width and depth based on your data, or?
Yeah, it's black magic, unfortunately. That's what a lot of neural, I wish I could. Now I will, over the next 2 sessions, will be talking about more specialized neural network architectures. So I didn't go into too much detail here, but the types we were looking at today were called fully connected neural networks, because they're, you know, if you look at all the images of these, you know, all the neurons are all connected to each other, and it's very, you know, everything is fully connected here. But for certain kinds of data, it will be more advantageous to take advantage of the fact that not all of these connections need to be maintained with each other, because we can use certain assumptions about the relationships between certain things. So the next session is going to be about recurrent neural networks, which build on the idea that there is temporal invariance within sequential data. So for example, the first step in time is more related to step 2 than it is to step 100. So we don't need to have the same number of connections between step 1 and step 100, as much as we need to just figure out, how do I transform from the first step to the next step? So that's how recurrent neural networks work. You might have, if you're working with image data, you might use what's called convolutional neural networks, which is instead taking the idea that use what's called spatial invariance, where it says, I want to learn more how is this part of the image related to everything that's immediately around it, and then you use frames like a small little lens that goes all across it that sort of is finding all those local relations more, because everything close to here is a lot more important for figuring out what's going on in that picture than comparing this pixel in the top right corner to the pixel in the bottom left corner. So that doesn't necessarily answer the questions about like how many layers and all of that, but it can be helpful in understanding like how to piece things together based on, like you said, what your data is. But unfortunately, usually I would recommend starting with like an existing model, I mean, depending on what your task is, but one that might already exist for a related application, and then you make changes to it yourself based on how that is. But unfortunately, or fortunately, you could say, there's been a lot of work into determining how these networks need to be trained and initialized and set up to perform at least to some base level on a type of task. And I guess one of the beauties of a lot of these different types of networks is that many of the things, once it's learned for something, can transfer well to other things. And while I'm not going to talk about them in any detail during these 5 sessions, many people are now experiencing this to a great degree, given that LLMs are so widely used. And that is based on, very similarly, on the idea that if you give enough data and you train a network well enough for such a large number of situations, there's a lot of things that can transfer over to a different set of problems.
Thank you.
Yeah, of course. I don't see any, I have a couple things on, okay, I think we're good. So I don't see anything on Zoom here, so I think we'll close things up. Thanks again, everyone, for coming, and we'll have another one in 2 weeks. Hopefully they'll have the screen fixed by then. So, great, thanks again.